Hello, my name is David Wiseman, and I work for Isograph in technical support and customer training. In this video, we're going to have an introduction to the AvSim module of Availability Workbench. Availability Workbench is a suite of analysis tools for things like maintenance optimization, RAM analysis, lifecycle cost analysis, viable analysis, and other things as well. Today, we'll be focusing on the AvSim part of the suite. This is the tool for RAM analysis, for system availability analysis. AvSim uses Monte Carlo simulation to simulate the failure, repair, and maintenance of assets in a system and model the way these outages and these events interact in order to affect the availability, capacity, and costs of a system. The analysis is based on a logic diagram, which can be either a reliability block diagram or a fault tree, and the failure, repair, and maintenance data provided by the user. So we'll begin by showing how we can build a logic diagram in the AvSim module. Now, as we mentioned earlier, the AvSim model is based on a logic diagram, and there are two different types of diagram that we can use, a reliability block diagram or a fault tree. We're going to focus on reliability block diagrams for this video. They are perhaps the most intuitive type of logic diagram for a RAM model, and they are the most commonly used as well. So we want to build a block diagram in AvSim. We begin by going to the Add menu, and we can create a new system. This is the object that will represent the system that we're modeling in AvSim. So I add a new system, and that will appear in the tree control. I can then double click on that, change its name and description, so I can provide a little bit of qualitative information about the system that I'm modeling. Click OK, and now we can begin to construct the diagram itself on the right-hand side. The diagram will consist of blocks that represent component failures, equipment failures, subsystems, and other events that might affect the availability of our system. Connections, which will represent the way in which these different events, these different blocks interact with each other. And of course, nodes, which will act as connecting points in our reliability block diagram. So I'll begin by creating just a few blocks. We'll go to Add, to Diagram, and a block. And then we can simply left click in the diagram area to add blocks at different positions. So we'll left click to add a block, maybe just add a few more, then right click and clear to go back to the regular cursor. As with the system, each of these blocks can be modified or edited by double clicking on them and changing their names. So this may be a component, perhaps component 1, component 2. Maybe this block represents a subsystem. This is a concept we will revisit shortly, but I will name that one maybe subsystem. So we need to connect these blocks together in a way that is representative of the system logic, how these blocks interact to affect the system availability. So I want to connect maybe component 1 and 2 in parallel, maybe to represent a redundancy, for example. In order to do that, I will need some points to connect my blocks together. These will be the nodes. So we will go to Add, to Diagram, Node. And again, left click where we want those nodes to appear. Right click and clear. And if you're unhappy with the position of an object, they can be selected and moved around fairly easily just by dragging them to different locations. So now I need to connect these blocks together. I can go to Add, to Diagram, and then I can add a connection. The program allows you to create either horizontal and vertical connections or diagonal connections. The difference is purely visual. It doesn't matter which one you select. It's just which one is perhaps the easiest to use in a given scenario, or which one would look the best. I will just choose horizontal and vertical, and then click where I want my connection to begin, and click where I want it to end. And in this way, connect all these different objects together. And right-click and clear again. So now the program will understand that if component 1 is failed, the system is still available because component 2 is available. But if both components 1 and 2 were to fail, then the system would be out of service. Similarly, if the subsystem were to fail, that would bring the system out of service as well, because this forms a bottleneck. So as mentioned earlier, we can have subsystems in our reliability block diagram. Let's say this block represents a subsystem and has its own internal substructure. We can select that block and click Page Down. And this takes us inside that subsystem block. And here we can add more blocks, maybe representing components or even individual failure modes of the parent block. And again, we can connect them together just to give us the logic. This is very simple logic, just a train of blocks where any one of them failing could result in the failure of the system. Of course, it could be more complex than this. You're not limited to series blocks in a subsystem. And in fact, the program will not limit the number of levels of subsystem you can have either. If I wished, I could select this block and page down again. I can have as many levels to my subsystems as I wish. So now that we have created a simple block diagram, now we can begin populating that with failure and repair and maintenance information. This information is provided to the program in the form of failure models. We can add a failure model via the Add menu, add a resource, choose Failure Model. And this brings up the Failure Model dialog. Here we can provide the program with information about how frequently a certain block might fail, how long it takes to repair, what kind of maintenance we're performing. If we go to the Failure tab for our failure model, we can enter failure data in one of several different ways. We could, for example, enter the data by hand, select a failure distribution, and then just type the information directly into the dialog. This you might do if you were, say, using information from a manufacturer's data sheet. They've provided a sheet with specs for a piece of equipment, including perhaps a mean time to failure. You could select maybe an exponential distribution and enter the MTTF directly. What if you don't have any information about the equipment? The manufacturer has not provided you with data, and maybe you don't have your own historical data to work from. In this case, you might choose the failure distribution wizard. Here, you can choose between 1, 2, or all 3 regions of a bathtub curve, enter some approximate information based on your own judgment or advice from colleagues or consultants, and the program will build a simple failure distribution based on the data provided. So for example, we might have a very simple failure behavior. We might expect that this piece of equipment just experiences wear out failures only. We can go to the wear out tab and specify that perhaps wear out begins immediately at the beginning of the lifetime. As soon as we start the equipment up, it begins to wear out. So we might set the age at which wear out begins to 0. And then we can specify how long it takes for most of the equipment to fail. So we might say that of a population of these kinds of equipment, most of them we would expect would have failed after about 5 years. I'm entering my time in hours. AvSim does not have a feature for specifying a unit. Instead, you are free to use any units you like. Typically, hours is the most commonly used unit, so that's what I'll be using here. Click OK, and you see the program enters the information you provided into the dialog. Ideally, you might have many years of work history. Maybe you have an ERP system like SAP or Maximo, or just Excel spreadsheets or Access databases where you have logged work history, when a piece of equipment was installed and when it failed, or when it was replaced as part of maintenance. The program has a built-in Weibull analysis tool, which will allow you to analyze this historical data and then use the results of that analysis as part of your model. That's what the Weibull set part of the dialog does. You can take the results of a Weibull analysis and then just pull that into your failure model. Now, the Weibull analysis is performed in the Weibull module of the software. We'll have a separate video that talks about that. But note that the Weibull module is supplied along with AvSim. If you have an AvSim license, the Weibull module is included with that. Once you've set up your failure behavior, your failure data, you may wish then to enter repair and maintenance data. When you create a failure model, automatically there will be a corrective maintenance task associated with that. There's our corrective maintenance task. So here we can specify perhaps, this is just the repair and it takes a certain amount of time to perform that repair. We can even specify an operational cost where appropriate. At the bottom, you can see it's possible to associate resources with a task. Resources are something we'll discuss a little later after we've done a simple availability calculation. We can also supply information about any maintenance that's taking place. For example, scheduled maintenance, planned maintenance, tasks that are performed at a regular interval that we can specify here and that will improve the condition of the equipment. Things like, say, lubrication or even a scheduled replacement of a piece of equipment might be represented as a planned maintenance task. Again, you can specify how long that task takes to perform, and you can add that to your strategy for this particular failure. It's even possible to model inspections. Inspections can take the form of fault-finding inspections, where perhaps you have a failure that has been marked as dormant or hidden, meaning that you might need to do an inspection in order to detect that problem when it occurs, and then trigger a corrective maintenance task in response. Or it might be that your inspection is a condition-based inspection. Here, we're inspecting the equipment and trying to determine if a failure is imminent. So think of things like a vibration analysis or checking for hotspots, things that are indicative of a failure that is about to occur. If we model a predictive task, we can provide information about how far in advance of failure we can detect a problem and what's the probability of detection, even how that probability changes in the approach to failure. And in the context of our model, if the inspection detects that a failure is imminent, it will trigger any planned maintenance tasks for which the secondary action checkbox is turned on the Advanced tab. Now, as well as planned maintenance and inspections, there are facilities for modeling the impact of alarms. A condition alarm operates a little bit like an inspection, only now instead of checking at regular intervals for an imminent failure, the alarm will monitor the system continuously. And again, you can specify probabilistic information about how likely it is that the inspection will detect a problem. You can model the impact of commissioning. So if you have a piece of equipment that undergoes early life failure and you want to do commissioning in order to mitigate that impact, then you can provide information about the length of the commissioning period, and the cost. You can even include the cost of a redesign. You might have 2 or 3 versions of a model representing different proposed designs of a system. Each of those designs might have costs associated with that change. You can include that cost and then compare the models, see which design is expected to perhaps give you the best cost outcome. Let's create this failure model. And there you see it appears in the tree control. We can now use that failure model with any block in our diagram. We can have multiple models. We can have model 1, model 2. We can rename them, of course, or we could use the same model. So, for example, I might say that component 1 and component 2 use the same failure model. So I just drag and drop those models onto the blocks. Those blocks will still be simulated independently of one another, but they should display consistent behavior. They will behave in a similar way to one another, as if you have identical components in a system. Now, for simplicity, I'm just going to use the same model for all my blocks. As mentioned earlier, you can, of course, have many failure models representing different types of failure with different repair and maintenance associated. But for simplicity's sake, I'm just going to use this one model. So we've talked about repair and maintenance, and of course we can associate costs with those tasks. But what about the costs, the impact of outages, the cost of lost production, for example? These things are handled with consequences. Consequences allow us to model the impact of failure and other outages. We can add a consequence via the resource menu. And consequences can be of 2 different types: total outage consequence or a loss of capacity consequence. The total outage consequence, of course, is the impact of a complete failure, a complete outage of our system. We'll take a look at this one first. So for a total outage consequence, we can specify a cost rate. How much does it cost per hour, let's say, while our system is down? We can also, if we wish, include a cost per occurrence, the one-off immediate cost of that outage. Think, for example, of a regulatory fine. It's even possible to model extended outage penalties. So if, for example, your outage lasted up to 24 hours or up to 48 hours, you could increase the cost rate by a certain value with each one of those milestones that the outage reaches. You can also specify severity. Severity is just a dimensionless value that indicates the seriousness of a failure. Safety severity, operational and environmental. These different headings are customizable. They can be modified in the options. But you might think of safety severity, for example, in terms of a number of fatalities that might occur as a result of a failure. So you might say, if a certain failure occurs, 10 fatalities are expected. You might enter a safety severity of 10 per occurrence. So I will create that consequence, and I can then allocate that consequence to any block in my diagram, and this includes the system itself. So if I double click my main system, I can select that consequence, click OK, and now whenever my system goes down during a simulation, the costs of that consequence will be incurred. So before we run an analysis of this model, we'll take a quick look at the options. Here we can specify some of the basic settings for our model. These include things like the lifetime of the system. So here we're just going to model this system over a 10-year lifetime, again, set in hours. On the simulation tab, we can tell the program how many simulations we wish to do. So in this instance, we will run a simulation of that 10-year lifetime 100 times, and the final results that we get will be mean over those 100 10-year lifetime simulations. Naturally, we could increase this, but in a real model, we would have to think about balancing statistical accuracy, which we would get from a higher number of simulations, against how long it might take to run the model. Because of course, the more simulations you do, the more processing time will be required. I'll click OK and run my model using the green light button on the toolbar. And pretty quickly we get some results. So the first tab in our simulation results shows us a breakdown of the lifetime costs, and we can make this a little more detailed just here. Now, of course, right now, the only costs we're getting are from the outages of the system. When the system fails or goes down, we incur these costs from the consequence. But we can also look at system downtime, and we can see that both for the main system and for the subsystem, where we can see how long the system is down for, how many outages we might expect, as well as other useful parameters. If we go to the Components tab, we can see availability data for the individual component blocks as well. And on the Consequence tab, we can see information about how often a consequence occurs, how long it's occurring for, and so on. So now let's take a look at making our model a little more detailed. We mentioned earlier that we can include the resources associated with maintenance. AvSim will allow you to create objects that represent the spare parts, the labor, and the equipment required to perform maintenance. So if we add a spare, for example, so this might be a spare component, and we can specify how much it costs to buy a new one. And we can even specify how many of these things we can store and what that will cost us, any logistic delays that are associated with getting that spare from storage. We can model local storage, off-site storage, like say a warehouse where we're keeping an additional store of spares. We can even model the supplier and any policies they may have with regards to the number that we reorder and any discounts that we're given. So click OK to create a spare. In a similar way, we can also create things like labor and equipment. Labor, of course, representing the skills required to perform the maintenance. Equipment, the tools that are used. So engineers and maybe cranes or trucks, the other things that they might use to perform the task. I will show you labor. I won't show both because the equipment input is exactly the same as for labor. We just keep them separate so you can see them separately in the results. So this might be an engineer. I can say how many engineers are available on site, how long it takes them to arrive for a task, and what the costs are associated with calling them out and having them working on a task. So I might say it takes them 30 minutes to arrive for repair, and it costs maybe $150 to call them out. And these resource objects can be allocated to maintenance. So if we bring back our failure model and go to the maintenance tab, we can double click a task and we can add the resources. We can add labor, say an engineer. We can even specify how many engineers we need. Similarly, we can add any number of spare parts that we need as well, and build up a list of the resources needed to complete this task. And when we run the simulation, the costs and the logistic delays associated with these resources will be accounted for in the final RAM model. Up to now, we've talked exclusively about outages, so a complete failure of the system, but it may be necessary to model the partial losses from a system or degradation. Perhaps the system might fall to 80% or 50 or 25% of maximum production. If you open up a block in AvSim and go to the Rules tab, here you will be able to specify what is the maximum percentage of system throughput that can be handled by this particular block. So I might say that each of my components, 1 and 2, can handle 50% throughput. I will show you a little later where in the options you can tell the program that maybe there is more than one product. Perhaps it's oil and gas, water and something else. It might be that there are multiple products going through your system. You can model up to 4 different products in AvSim with separate custom units. So I will set that to 50% for each of my components here. Notice also that it is possible to model things like hot, warm and cold standby. What kind of behavior you can expect from a component when it's not in service. For example, cold standby would mean that if the component is not in use, then it would be impossible for it to fail or to wear out. Whereas warm standby would allow you to modify the extent to which the component can fail or age while in standby. We'll keep them both set to the default mode of hot, which means it will just always behave as if it's operating. Now, obviously, if we're going to model degradation, production loss, we might want to model the costs associated with those production losses. So we can do that by creating a consequence to model those losses. Now, I could create another consequence for this if I needed to. I might just edit the one I already have. So I'll open that up and I will make it a loss of capacity consequence instead. I will go to the cost tab, and now, rather than just setting a straightforward cost for the outage, I can specify how much it costs per unit loss of capacity. So I might say that for every unit lost, for every percentage lost per hour, it costs me 100. But that if I say drop below 50%, if I fall below a 50% target production, that might increase by a further 50% per hour. And again, as you can see, it would be possible to set these values for up to 4 separate products. I'll click OK to make that change. And before we run the analysis, just a quick look in the options again at the Products tab to show you where you can specify how many products there are, and if you wish, customize the maximum capacity and the unit associated with that. So if we run our model again, you can see now we get slightly more detailed costs because now we can see things like spare purchase cost and labor costs as well coming from our resources. If we look at the system, you can see now we're getting a capacity as well. We can see the mean capacity of the system is 99.94%. And we now have tabs also for spares and labor, showing us how many spares we're using and what that will cost us, and how often we're calling out our engineer and what the costs are associated with that. Now, for more advanced models, it might be necessary to implement maybe a mission profile. Perhaps the performance of the system changes depending on what point in the lifetime has been reached. Or perhaps there is some dynamic behavior going on in the model. Maybe one component has a certain specific dependency on another. AvSim has a rules facility that allows you to model this kind of behavior. So let's show an example. I'm going to create some phases. Phases are periods of a lifetime during which we can apply different conditions. So I might say add a phase, and maybe this is years 1 to 5. So that's the first 5 years of the lifetime. I just specify the duration here and create another phase, and perhaps this can be years 6 to 10, so the remainder of the lifetime. You can have as many phases as you want. You can even have concurrent groups of phases by right-clicking, creating phase groups and adding phases to those groups. So you could have a month-by-month phase regime running concurrently with a year-by-year phase regime. And if the total duration of your phases is less than a lifetime, that's fine. The program will simply cycle through the phases until it reaches the end of the life. So now that I have these phases, I can say double-click a block, go to the Rules tab, and I can add a rule. So here you can see the rules associated with a block. You can see, of course, there are lots of things I could change by phase, like capacity or the load factor. Load factor, I might say, perhaps during years 6 to 10, the load on the system increases by maybe 10%, meaning that the failure rate of the component will increase by 10%. The load factor is a multiplying factor that adjusts the failure rate. So I can click OK, and I can add more rules if I wish. As you can see, there are many rules by phase, but there are also rules by state as well, allowing you to, for example, change the load factor by state. I might say that if block 2 is in a failed state, the load on my component block 1 increases by 50%. Maybe component 1 has to work harder if component 2 is failed, meaning that component 1 is more likely to fail as well. So I can create these rules to modify the way in which objects in my system behave, depending on what's going on at a given point in time. And you're not limited to block rules. There are rules for maintenance tasks, which will allow you to trigger or inhibit tasks under different circumstances. There are rules for consequences that allow you to maybe adjust the costs by phase. So there are rules throughout AvSim that allow you to really closely control the way different aspects of your model behave. So perhaps before we run an analysis, we'll take another look at the options, and we'll go to the Importance tab. Here, we're going to select a consequence to act as the reference point for an importance analysis, meaning that we will be able to learn which blocks are contributing the most to different reliability parameters, number of outages, availability, cost. Where are the bad actors in the system? So I'm going to click OK and run my model again. So this time, you can see there is a Phases tab where I have now a breakdown of my costs by phase. I'm going to switch to the plot view now. And you can see the program can create profile plots showing how costs and other parameters are broken down across the lifetime. But I'm most interested here in the contribution plot, which can show me, for example, how much each different component contributes to cost. And I can see this subsystem 2 block seems to be the biggest contributor. So to end the video, what we'll do now is take a look at some of the reporting options that are available in the software. You can access the report via the report button at the top right. The report designer, which is what we can see now in the window, allows you to open one or more report templates, which will populate with data from the current project. These templates are customizable, and you can create your own reports as well. We will have a separate video on the different features of the reporting tools. For now, I'll just show a couple of examples of the kind of reports you can get from an AvSim model like this one. So I will open a report, and we'll go to maybe AvSim predictions first. And we'll look at maybe the reliability block diagram importance rankings. Open that report, and you see this is giving us a kind of text breakdown of the information that we saw in the plot earlier. Obviously, there are other reports as well showing availability data for the different components and subsystems, as well as a wide variety of other information as well. Let's open maybe a plot report. If we go to AvSim plots, in fact, we could open the same information, but this time displayed as a graph. So there is our contribution plot. Again, a bar chart just showing how much each block contributes to overall cost. And of course, perhaps the most commonly used kind of report, the diagram. So if we go to AvSim diagrams, open that report, you can see there's our reliability block diagram spread across two different pages because, of course, we have two layers of subsystems. As mentioned earlier, all of these reports are customizable through design mode, and naturally they can be published, they can be printed off, they can be published directly to Microsoft Word, to PDF, or to a text file like CSV that you could even open in Excel. So thank you very much for joining me for this video. We will of course have other videos on other parts of Availability Workbench, and I look forward to speaking to you again soon.